So, we have been discussing about this microsystem for micro robotic related applications. Like we have been discussing more on the manipulation related aspect in the current modules. So, we have seen the different methodologies which are involved with reference to magnetic, with reference to acoustic, with reference to optical tweezers, etc. in detail, and we have also seen an AFM, how AFM has been catered as a kind of a robotic system for a specific applications. Now, in today's lecture, so we will discuss about this integrated nano tool carrier. So, as far as these nano tool carriers are concerned, it's a kind of a high precision device designed to hold and manipulate nanoscale tools for microprocessing, for microfabrication and material processing. So, the major nano tool carriers used in the fabrication characterizations are the MEMS based tool carriers and the vacuum based tool carriers. Now, if you try to focus on the different application perspective point of view, so such kind of nano tool carriers are efficiently used for atomic force microscopy, nanolithography, biotechnology and medical applications, nanometrology and precision measurements. Ultra precision machining are some of the key applications which are projected by these integrated nano tool carriers. Now, as far as in these nano tool carriers are concerned, now let us take this MEMS based nano tool carrier. In the case of MEMS based nano tool carrier, we have silicon on insulator, where we have a silicon layer, silicon oxide and a silicon wafer. So, over the silicon wafer, we have the silicon oxide and the silicon layers which are being placed. So, as far as these tool carriers are concerned, so the tool carriers can be fabricated as a MEMS device by using silicon on insulator, that is SOI. So, in this SOI is a 3-layer structure with silicon wafer base coated with SiO2. On top of insulating SiO2 layer is a thin coating of silicon. So, this final structure is created by a DRI, which is a kind of a silicon etching, and a SiO2 etching process is deployed in this particular system. Now, when we try to consider a kind of a micro capacitive sensor, this device provides the mean for the actuation and sensing via electrical signals. So, if you try to look into the overall construction of it, so we have a kind of a structure, like it's a kind of a like a comb drive actuator kind of structures. We have multiple electrodes which are being placed, and the movement of the multiple electrodes are appropriately connected with a kind of a capacitor arrangement which is available over here. So, as far as in this capacitive sensors are concerned, so if you closely observe in this capacitive sensor, so there are two capacitor configurations are there. So, one capacitor configuration sensor is over here and the other capacitive sensor configuration is over here. Both the capacitive configurations has a load sensor beam. So, in this load sensor beam, the capacitors are connected, and then you have a kind of a arrangement which is placed over here, and then there is a kind of a specimen gap which is available. This specimen gap will act as a kind of a reference gap. Then in addition to this, we also have a thermal actuator in place. So, these thermal actuators are efficiently used for compensation related aspects. So, in the case of this micro capacitive sensor, the device provides the mean for the actuation and sensing via electrical signal. It consists of a thermal actuator. It has a 2 interdigitated capacitive sensor, a load sensing beam, a specimen gap for observation in the temp. The MEMS devices are fabricated by MEMS cap using a kind of SO-MUM process, which is a kind of a very specialized process. So, the monocrystalline silicon structural layer is patterned to create the required component of the device, while the substrate is patterned and etched from bottom side to the oxide layer to create a kind of a freestanding structure for the TEM imaging purposes. Now, when we try to look into the overall functionality of this thermal actuator, the thermal actuator consists of 10 pairs of inclined beam, provides a driving displacement to the device by resistive heating. So, the displacement of the thermal actuator is controlled with the input voltage which is applied across the beams, which is being recorded with reference to the capacitive actuator. Now, as far as in this microcapacitive actuators are concerned, a very large heat sink is provided between the thermal actuator and the nearest capacitive sensor. So, the distance of the actuator from the specimen gap is in the order of 1.5 mm. This heat sink limits the temperature increase near the specimen gap to 0.07 degree Celsius per 10 nanometer displacement of the thermal actuator, which means as and when there is a temperature rise is there, so appropriately there is going to be a kind of a 10 degree Celsius. So, 2 air gaps on each side of the capacitive sensors are filled with the epoxy groove. So, these rigid epoxy bridge provides an electrical isolation between the thermal actuators, a capacitive sensors like CS1, which is nomenclated as CS1 and CS2. So, one of the epoxy bridges connected CS1 to the thermal actuator, while the other it connects to the specimen gap CS1. Therefore, it measures the displacement of the thermal actuator XA. So, the other capacitive sensor CS2 is rigidly connected to the load sensor and hence measure the displacement of the load sensor XLS. So, this is a kind of a configuration which is like a kind of a system which is mainly meant for a kind of a nano tool carrier for with microcapacitance as a base. Now, let us take another example which is a kind of a micro container and a micro transport mechanism. So, as far as in this micro container is concerned, the ratcheting structure convert a reciprocating displacement of an electrostatic comb drive actuator to continuous unidirectional straight and turning movement of the micrometer scale object. The force induced from the electrostatic comb drive actuator pushes the ratchet rack inwards, causing the driving wing to move inwards. So, this is a kind of a driving wing and this is a kind of a reverse wing and this is a kind of a backbone arrangement. So, this ratchet rack will try to push it and then the driving wing and the reverse wing will appropriately actuate it to get the required characteristics. So, like this is a kind of a, even though this is a kind of a micro container, this is more to do with micro transportation mechanism. It's a kind of a mechanical systems which are being deployed for appropriate movement or for the appropriate collection. So, the force induced by the electrostatic comb drive actuator pushes the ratchet rack inwards, causing the driving wing to move inward. So, as a result, the container moved object is moved forward, and when the force is removed, the container will not move backward due to the ratchet mechanism of the anti-reverse wing. So, this is a kind of a one-way mechanism which exhibits over here. This ratchet wing will be helpful for us to give a kind of a increment displacement to the system. So, with reference to increment displacement, appropriately we can expect a kind of a movement which exhibits over here. Now, let us discuss about this vacuum based carrier. So, as far as in this vacuum based carrier is concerned, so we have a gate arrangement, then there is a gate oxide which is there, a source and a drain arrangement which is available. So, this in this vacuum based nano tool carrier is a kind of a precision system which is designed to transport, position and manipulate a nanoscale tool or objects using a vacuum source. Example, as vacuum based tunneling transistors or nano vacuum tube or a vacuum grippers, etc. So, ideally it is more to do with the vacuum. So, a nano gap vacuum tunneling transistor, it is fabricated on a silicon substrate with a thermally grown SiO2. The gate electrode is patterned by an electron beam lithography which is so precise. So, the charge dissipating agent was coated to minimize the electron beam charging effect for the nano gap. So, the gate material of CR, AU are deposited using a thermal evaporation system and using a lift off. So, in fact, related to lift off we had discussed a lot. We have discussed about this micro 3D printing technology which is considered to be one of the key aspect in fabricating such kind of vacuum based system which has a potential application towards a nano tool carrier related applications. Now, as far as in this vacuum based carrier systems are concerned, so we have a nano vacuum tunneling transistor. So, the SiO2 which was used as a gate oxide it was deposited using a kind of a plasma enhanced chemical vapor deposition process. So, it is a kind of a PECVD process which which gives a kind of a high quality crystal for based on our requirement. And then there is going to be a source and a drain electrode. We are also patterned using this EBL. It is used to obtain a gap that was a several tens of nanometer in size. So, for the electrode material, W was deposited, that is the tungsten was deposited by a magnetron sputtering system and then appropriate lift off, so that you can fabricate a kind of a layered based structure on this particular system. In addition to this, all contact pad of the electrodes were fabricated using a kind of a photolithography process, deposited using the same material and method. So, as far as in this particular process, the electrodes are fabricated in such a way that the photolithography and the deposited layers using the same material are established in a particular fashion for an appropriate application. Now, an extended version of this vacuum based carrier is concerned, there is a concept called nano vacuum tube. So, as far as in this nano vacuum tube is concerned, so we take a similar configuration where there is a drain, source, gate and a gate oxide, and a vacuum chamber is placed, and appropriately a nano tube, this vacuum chamber is used as a kind of a nano carrier tool. So, the vacuum chamber is a kind of a tubular structure on top of the vacuum transistor. A wall of the vacuum chamber is silicon oxide deposited with PECVD. The nanoscale hole is patterned for the vacuum cylinder using this electron beam lithography, which we call it as, this is electron beam lithography. The vacuum chamber is sealed by a thin film deposition using a thermal evaporation system, and then an AL is used as a kind of a vacuum sealing material with 400 nanometer thick. Okay. So, due to the photovoltaic and a kind of a photoelectric effect, semiconductor device suffers from an abnormal behavior when the light is exposed. Even the semiconductor device can be damaged by a kind of a high energy light. So, these nano vacuum tube can effectively seize these damages, and appropriately it can be used for a kind of a application which has a potential application towards this nano carrier tool. So, this is one combinations where a nano vacuum tube has been effectively used to seize the damage. Now, let us also discuss about this integrated nano carrier. So, as far as this nano tool carrier is concerned, like vacuum based carriers are considered to be a kind of a vacuum grippers. Like these vacuum grippers are a kind of a glass pipette, are either made from a soda or a borosilicate glass tubes. So, like grippers are produced by heating and pulling the hollow tube simultaneously. So, here in this particular case, so we have a kind of a tube which is available over here. So, in this tube a kind of a vacuum is created. So, this vacuum is used for moving a micro object back and forth. So, what happens is the direction of the movement of this micro object is well manipulated with this vacuum. So, that is, so we have three different modes of operation which are being well represented over here. The first operation is a kind of an approach operation where the vacuum tube is brought near to the micro object and then a suction is being initiated. So, this is a kind of a approach behavior where the vacuum tube is brought near to the micro object. When it is placed near to it, so there is going to be a suction which exhibits. This suction is for holding the particular object, and then there is going to be a retraction, that is release of the particle. So, these are some kind of combinations which are being exhibited towards the kind of a different manipulation condition, micro manipulation condition. Now, let us discuss about one of the key aspect, that is the autonomous programming of these micro assembly robots. So, as far as in this particular case is concerned, so we have seen several like configurations of these micro assemblies. Like we started with this AFM, we had an interaction with acoustic based system. So, we have studied the different methodologies which are involved in it, starting from a gripper, a magnetic assembly, a magnetic micro robots, grippers, light, optical suite, tweezers, acoustic field and direct self assembly. In all these cases, if you see, so there is going to be a kind of a magnetic field, or there is going to be a kind of a field which exists. So, based on the field, so appropriately the manipulation is exerted. Either your manipulation is on a micro scale or in a nano scale, appropriately your exertions are being controlled. So, in fact, we have, that is the reason we had some discussion about the AFM. So, AFM is a kind of a characterization tool which is effectively used for a kind of a micro manipulation aspects. So, in the case of an AFM tool, we have seen a different modes, the overall functionality of the AFM and the overall characteristics of the AFM, how these AFMs are deployed for different applications, and then we have also discussed about this overall feedback systems which are being deployed in this AFM related applications. Now, usage of this AFM in the form of a nano and fiber pulling is also investigated, and there are other modes of systems have also been investigated, like polymer drawing, then like flame or heated taper drawing, and then we also had a discussion about this gas absorption based spectroscopy, application of these fibers in gas absorption based spectroscopy, Mach-Zehnder interferometers, and then in the case of gratings, resonators, etc., couplers we have discussed. So, we had a good discussion on the optical tweezers, especially on optical manipulation. What are the different configurations of optical manipulation? This is a conventional optical tweezer system with acoustic deflection, and then we also have a kind of a holographic optical tweezer. So, using which we can map a multiple system in this particular orientation. And then as far as micro and nano tool is concerned, so appropriate tool carriers are deployed. So, one is a kind of a vacuum base, another one is a kind of a tunneling base, third one is a kind of a transportation, mechanical transportation based mechanism which exists, and then there are certain amount of capacitive sensors are there which exhibits, and then so we also have a kind of vacuum kind of arrangement which is used for appropriate vacuum suction. Now, let us discuss one case study which is towards autonomous programming of micro assembly robotics. So, like due to the strive in the miniaturization to systems and growing field of optical technologies, and micro assembly is becoming a kind of an interesting and an important micro assembly. So, micro assembly is characterized by the challenging process that requires a kind of a submicron level position accuracy regardless of the modeling and calibration errors in the manipulator system. So, there is a need to go for automation of this process, or need to have an understanding on the automation of this process, which requires not only a profound expertise, but the process itself also requires a highly trained person in the field of programming. So, we will be discussing about the autonomous programming combining with the kind of an intuitive programming approach with intelligent and self-learning algorithm, how it is being demonstrated in an actual condition. So, let us discuss about the abstraction level of this robotic programming. So, in the case of an abstraction levels of robotic programming. So, one is related to the usability. So, when we try to classify, one is the abstraction level and the other one is the user input. So, under the abstraction level we have the product, process, tool arm and the joint. Under the user input, we have the product description, we have the task sequence and parameters, a Cartesian space trajectory, and the joint variables. So, we have the usability in place. Then we have the granularity of control. Okay. So, when we try to look into this programming of these industrial robot, so traditionally it requires a kind of a high level of expertise, which makes it to setting up a new process, which is a kind of a time consuming and expensive process. However, there are several approaches have been made to make a robotic programming more intuitive or even autonomous. So, the principal approach entails elevating the abstraction level in the programming to enhance the intuitiveness for the user and the subsequently diminishing the need for an extensive programming expertise. So, by considering these parameters, so appropriately we can have a control over the programming expertise. Within the domain of the intuitive programming, its emphasis is placed mainly on the abstraction level of the process. So, here skill serves to encapsulate the textual code. The skill sometimes also called the function modules or functional blocks, representing the basic functions of the robot, example like pick and place or gripping, so that the user inputs is on the kind of a task level which is being established over here. Now, similarly, when we try to talk about the simulative framework for microassembly and intuitive task programming, so there are different methodologies which are being deployed with reference to industrial robotics and programming of microassembly robots. This still requires an expert knowledge. So, where it requires a kind of a current state of intuitive programming for a kind of a microassembly robot. Now, as far as in this microassembly robot is concerned, so let us when we try to consider a kind of a autonomous microassembly robot, let us discuss about the key parameters or the key aspects which we may need to plan when we are trying to create a roadmap towards a kind of an autonomous microassembly robot. So, ideally it involves, so let us consider the different programming configurations which will be considered for a micro robotic application. One is a kind of a manual programming, then we have the assisted programming, intuitive programming, and autonomous programming. Okay. So, in this particular case, we have 4 different sets which contributes to it. So, one is called as the function module, and the other one is called as a holistic simulation, and third one is called as a process manager, and fourth one is the data management. So, in this particular aspect, so we have two different inputs which we need to take it up into consideration. One is a kind of an abstraction level and the other one is the user input. Okay. So, let us discuss one by one with reference to their applications or with reference to their overall characteristics. So, as far as in this particular case is concerned, the current approach not only from the field of industrial robotics, but also the microassembly address several aspects aiming to achieve an autonomous programming. So, analyzing these aspects, there are four fundamental aspects essential for the realization of autonomous robot programming. So, these are in general applicable not only in microassembly context, but also across the broader spectrum of the industrial robotics. So, there are four key enablers are there which we have discussed over here. One is called as a function module. The foundation of intuitive and autonomous programming are function or skill representing the functionalities and capabilities of microassembly systems. This comprises robot as well as sensor function parameterizing themselves using a self-learning algorithm. Now, when we discuss about a kind of a holistic simulation, so it is mainly meant to enable the offline programming and self-learning operations. A simulation of the whole assembly is necessary, including the robot, robotic peripherals, sensor systems and the components to be assembled. And the calibration methods are used to reduce the gap between the reality and simulation, ensuring a seamless transfer. This is particularly relevant in the case of a microassembly, as even a small deviation can have a major impact on the quality of the assembly. Now, let us discuss about the data management. As far as the data management perspective point of view, it is mainly meant to facilitate the data flow across the different modules and their functionalities. A centralized database is mandatory. Part, machine and process related information can thus saved and accessed conveniently. So, the data management module also includes the functionalities for monitoring and visualization of information. Finally, the database serves as an interface for human or software related inputs and output to the framework. Now, we also have the autonomous process manager, which is in the autonomous mode over here. The process manager is needed to process the information of a given task and to initiate a representative data which flows between the different modules. So, in its form, it will represent the artificial intelligence of the system, that the process and the input and the output data. It extracts the relevant information and forward it to the different modules accordingly. It manages the process knowledge and the process sequence as per the requirements. Okay. So, these are some of the kind of a framework which exhibits with reference to the self assembly micro robot perspective point of view. So, this is a kind of a larger picture and the larger framework which is discussed from a research paper, and then so this will give a kind of a roadmap, so that in which direction appropriately programming needs to be evolved. Okay. So, these are some of the references which are used for this particular module on microsystem for micro robotic system. So, the next microsystem for micro robotics will be more focused towards integration, which we will be discussing in the upcoming class. Thank you.